6, improper integrals. And the idea of an improper integral is an integral that is a definite integral. It includes the boundaries. But one of two things can happen. Either, first of all, either plus or minus infinity is one of the bounds, or the other way that an integral can be improper is if the function in the integrand, so if I have finite boundaries, numbers, integral from a to b of f of x dx, if our function in the middle is unbounded somewhere within our boundary interval. F of x is unbounded somewhere within the interval from a to b. So these are the two different ways that we could have an improper integral. In last class we looked at examples where we had the boundaries being infinity or negative infinity, or in one example we even had negative infinity on the bottom and positive infinity on the top. And the question became, okay, what happens if we replace that infinity with a number and then eventually allow that bound number to go off to infinity? Is the amount of area we get a finite amount, in which case our integral converges? Or is the amount of area that we get an infinite amount of area, in which case our interval diverges? Okay, so I want to look at one or two examples of this second type of improper integral today. Okay, so here's our first example. So let's take a look at the integral from negative 6 up to 2 of x minus 2 raised to the negative 2/3 dx. Okay, so you're walking down the street, this integral jumps out at you. It's a definite integral. I've got boundaries on it. And it jumps out in front of you and says, here I am, analyze me. And so we look at it, and at first glance, I might say, oh, well, I can just do u sub, do my antiderivative, plug in the boundaries. However, this guy's actually masquerading. Okay? This is, in fact, an improper integral. Why is this integral improper?
Because when you put in 2, it's 0.
Yeah, so when we put in that boundary of 2 into our integrand, we get 0, and which itself is okay. The problem is that we have that negative power up here. So really, when I rewrite this integrand, when I think of this as the integral from negative 6 up to 2 of 1 over x minus 2 raised to the 2/3, really the x minus 2 is part of our denominator. And so when I plug in x equal to 2, I get a 0 in the denominator, which we never want to have happen. So when x is equal to 2, 1 over x minus 2 to the 2/3 is undefined. Okay. All right, so I've got this integral, and so now I'm looking at this, and my top boundary is this one that's a problem. So I'm going to circle that one and say, okay, that's our bummer, and I might even go ahead and graph this function in my calculator. And if I do graph this function in my calculator, here's what it looks like. Y equals 1 over x minus 2 raised to the 2/3, and you should check this on your own. But if you graph this function, you should end up with a vertical asymptote at x is equal to 2, and a function that looks something like this, moving off to the left, and something like this, moving off to the right. Now, we are interested in this function starting at x is equal to negative 6, so we'll just stop that right there. So negative 6 up to a value of x equals 2. So we're interested in the area under our function starting at x equals 6 and ending at x equals 2. The problem is, when I end at x equals 2, I could potentially have kind of half a volcano here where my area is spewing out the top. And so that's our improperness here. Okay, so the very first thing we want to do is to deal with this unlucky boundary, okay, this value where our integral becomes improper. So I'm going to replace that 2 with some letter. So I'll have the integral from -6 up to some letter, whatever letter I want to choose. That was a 2, so maybe I'll choose a t. So from -6 up to t of 1 over x minus 2 raised to the 2/3 dx. Now, by making this a proper integral and saying, oh, I'm not going to actually let that top boundary be 2, I need to pay a price. And my price is that I'm going to take the limit as t approaches 2. So what we're doing is we're going to cut off this integral somewhere close to 2, but not quite at 2. And then we're going to move that right-hand wall until we hit the value of, almost the value of t equals 2. Now, we won't actually hit t equals 2. We're going to get as close as possible, but we're not actually going to hit it. Okay? So technically, when you're talking about limits, if I write this limit down here, the limit is t approaches 2, that's actually a limit from both sides. Right? So in this case, I'm really only looking at the limit as t approaches 2 from the left-hand side, from the left-hand side. And so I really want to write the limit as t approaches 2 from the left with a little negative sign up there. Okay, any questions about this so far? So I've taken my integral, which was improper because our top boundary forced us to have a 0 in the denominator, and I've rewritten it so that my top boundary is no longer that bad number. It's now a number t, and I'm going to allow that t to get close to 2, but not actually hit it. Okay, so now let's analyze this integral. So I'm going to ignore the limit symbol for now, and I'm going to analyze taking the antiderivative. And so if I'm thinking about this, take a look at this integrand here and think about what technique you would use. Don't say it out loud just yet. But ask yourself, what would my first step be? Okay, now turn to your neighbor and tell your neighbor what you think. Okay, anybody have any ideas? Any thoughts?
Did you bring it up top?
Yep.
Okay, so yeah, we might go back to our original. It was nice to see this, the 1 over x minus 2 to the 2/3, so we could see that our integral was improper, but you're absolutely right. What we really want to think about is the integral from -6 up to t of x minus 2 to the negative 2/3 dx. Okay. What might we do after that?
Integral it?
Yeah, u sub seems like a really good option. We have fancy inside parentheses, and so I might allow my u to be equal to x minus 2. Okay? So u sub, my whole process here, I've got du over dx, which is equal to 1, which tells me that dx is equal to du. And additionally, I can change my boundaries on here if I want to. So when x is equal to -6, then u is going to be -6 minus 2, so that's -8. And when x is equal to t, then u is equal to t minus 2. Okay, so we have our limit as t approaches 2 from the left of the integral from -8 up to t minus 2. And then we have u to the negative 2/3, and dx is equal to du. written our entire integral in terms of u. My boundaries are u boundaries now. So I can go ahead and take my antiderivative. Any questions about what we have written up here? Okay? So I'll add 1 to my power. I still have my limit as t goes to 2 from the left. Add 1 to my power gives me u to the 1/3, and divide by that new power divided by 1/3 is the same as multiplying by 3. And then we'll evaluate that between -8 and t minus 2. Okay, so I'm going to plug in my top boundary here. So I end up with my limit as t approaches 2 from the left of 3 times t minus 2 raised to the 1/3 minus 3 times -8 to the 1/3. All right, so some analysis in here. If I want to simplify this here, -8 raised to the 1/3. If I wasn't sure, I could type it in my calculator, but that's the cubed root of -8. So -8 to the 1/3 is cubed root of -8, which is -2. What's that? So if you're thinking of even powers. So with the odd powers, -2 times -2 times -2 is going to give me an odd number of negatives. Okay, so we've got the limit as t goes to 2 from the left of 3 times t minus 2 raised to the 1/3 minus 3 times -2, so that becomes plus 6. Okay, any questions or comments about this so far? We've finished the antiderivative part, but we have not analyzed the limit. We've not taken care of our improperness yet. Okay? So at this point, we need to deal with the limit. So we're allowing t to get closer and closer to 2 from the left. So if I think about what's happening here, t is getting closer and closer to 2. I'm thinking about 1.9, 1.99, 1.99999, 1.999999999, and even closer than that. So what is happening to this t minus 2 inside the parentheses as t gets really close to 2? Yeah, this value is approaching 0, and the cubed root of 0 is still 0. So this entire term is going to go to 0. And so the 6 here, as t approaches 2 from the left, absolutely nothing happens to that. So we're left with 0 plus 6, which is a value of 6.
I'm sorry, could you explain that, how you got 0 there?
So what I'm looking at here is so the limit as t approaches 2 from the left of 3 times, and I'm going to write this as the cubed root of t minus 2. That's the same as t minus 2 to the 1/3. And so what I might do is say, okay, I'm going to look at the part that's just the t minus 2 inside here. As t gets close to 2, this value inside here gets very close to 0. Think about t being 1.9 or 1.999. And so this term, t minus 2 goes to 0, which means that the cubed root of 0 is still going to be 0.
Thank you.
Good. Okay, other questions about analyzing our limit? All right, so our conclusion here is that the integral from -6 up to 2 of x minus 2 raised to the 2/3 dx converges to a value of 6. So what we're saying is that if we want to paint a wall that has the roof or the ceiling in the shape of 1 over x minus 2 to the 2/3, and we want to start at x equals -6 and end at x equals 2, well, we really only need 6 square units, or enough paint to cover 6 square units, although we need a mighty tall ladder to get the last little bit here off here at the right-hand side.
So can you
So minus 2/3.
Yes, thank you.
can you explain what converges and diverges again? I'm sorry.
So whenever your final value down here comes up to be a finite number, then we say the integral converges, and it converges to that number. If your final answer comes up to be infinity, positive infinity or negative infinity, the integral diverges.
So do we want our final answer when we're doing these to look like that conclusion?
So chances are really good that the way that I will ask a question for an improper integral would be evaluate the improper integral and determine whether the integral converges or diverges. If the integral converges, determine what it converges to. So somewhere I would want to see that you identify that the integral converges, and I'd want to know what your value was. So if you stopped here and said equals 6, comma, converges, that would be minimally, that's enough. But I do want to see the word converges, and I do want to see the value.
Okay.
They have problems like that in the blue too, on the homework that you assigned.
Yeah, so you mean where we had the finite boundaries?
And they ask you to see if it converges or diverges.
Yep. Yeah. Okay, other questions about this example? Okay, so in terms of our exam, let me see if I want to look at one more. Actually, I do want to look at one more example here. But before we do that, in terms of, okay.
What if your interval goes over the like broken in the middle? Is that a different strategy, or are we going to have to deal with that?
That's a really good question. And so what would happen there is that we would have to say, so for example, let's say that our integral went from -6 up to 3. In that case, the first thing is that you want to do is say, okay, does my function blow up somewhere within my interval? The answer is yes, at x equals 2. So we actually have to set up 2 separate integrals. One that goes from -6 up to 2, and then a second one from 2 to 3. And then we'd have to analyze each of those improper integrals separately. Take the limit as t goes to 2 from the left, as t goes to 2 from the right. Okay.
So in an example like that, where what if it converges and diverges?
Good question. And the answer to the question was, what if when you break up your integral, you end up with one of the integrals diverges and the other one converges? If any part of your integral diverges, the whole thing diverges. Okay, so if you break it up and part of it diverges, then all of it diverges.